Now it turns out it's quite hard to find solutions, exact solutions, and this you realize even if you just do a Rosler model or something. You realize that finding exact solutions is not really trivial, even in few dimensions. So for that reason, I felt we should look for a problem where we actually have very good intuition, very good knowledge, similar kind of equations. And that problem is fluid dynamics, which is described by Navier-Stokes equations, which are also rather simple. They have one nonlinearity. So mostly they're linear, but there is a nonlinear term. And now, at Georgia Tech, you're in a good place because everybody on this campus, except people in the business school, solved some equation like that. They do it in aerodynamics, they do it in environmental engineering, biology, mathematics, every place, because, this is an engineering practical school. So there's a great deal of intuition, and we actually have some world-acknowledged masters in some aspects of fluid dynamics on this campus. So it's a good place to be in. Even in this house, we have very good experimentalists. So, why would you do this? It has nothing to do with, as far as we can tell, there might be something to learn from fluids to the field theory of Young-Mills and gravity, but they're quite different in technical details. But if you can make some advance on that, you are in pretty good shape. Because even though you're not solving a problem that Indiana Jones cares about, you're making planes burn less fuel. You're making all kinds of practical problems can be solved if you have detailed understanding of solutions of Navier-Stokes, because having detailed understanding also will give you a detailed access to control of their behavior, and, understanding of what you can and cannot control and cannot do. So it's a difficult problem technically because we have to learn a bunch of things, but here we're in a good shape, and collaborating with people who really care about fluid dynamics, it turned out that this picture can be implemented for fluid dynamics. At least, again, now it's only for pancreatic fluid dynamics and not for brain fluid dynamics, because it works for systems that plumbers care about, which is, pipes, and not very big, stuff like that. But it doesn't, we are out of ideas when things get very crazy and very turbulent, etc. Then only tools we have still are only statistical guesses. But there is a whole regime in which we can use these equations, and we can solve them exactly just like we solve things for spectrum of hydrogen to arbitrary accuracy, and we can make predictions. So I can check one thing off. I can say that we have several examples now, classical solutions that maybe or maybe not dominate path integrals. That has to be seen, but we have no idea. Unless you try it, you'll never know. So it works for quantum mechanics. We do not know where it's going to work for quantum field theory. But while we are learning, we can solve lots of useful problems and bring some useful technology to other similar problems. So now, how do I imagine this could work? It sounds totally impossible, because even the trace formula was, unthinkable to unspeakable. On one hand side, we had something to do with this partition function. I mean, it didn't look like that, so you can't recognize it in this notation, but it's very close, in some sense, close to our zeta functions. We had some formula that said the spectrum, which is infinitely, it was complicated, and we don't know how to compute it. In lattice gauge, we can get 10 eigenvalues, which are called 10 elementary particles or something. We don't know how to compute this. On this side, this is supposed to be an infinite sum of classical solutions, or classical solution that repeats, and then computation, and then something are observable. But the main thing is that there's an infinite sum of these things. So it's very useful to train on very low-dimensional silly models like Lorentz, one-dimensional maps, etc., to realize, yes, this is infinite-dimensional, but, for example, there are infinitely many Fourier modes, but when we analyze sound, we only need something up to 40, maybe 20 or 40 kilohertz, and not beyond that. So there are ways, once you go into details, there are ways of truncating these sums. So now we have found some technology that tells us how do we systematically go and look, if you find one exact solution, how we find more. So we learned that they have unstable manifolds, and that close to them there will be more solutions, and that once we set it up, we can produce whole energy. Then, very important in formulating this theory is the principle of gauge invariance. So that's underlying both the general relativity and the quantum field theory of any variety that we do today, saying that locally we can choose, we can use the symmetry of the problem to choose coordinates every place in space-time when doing our calculations. And that we cannot do calculations unless we do gauge fixing, which means take one set of coordinates and just work in it, which in this course was called slicing. We have checked off symmetries. In some cases, we know what to do about this gauge invariance. That doesn't mean that we know how to do it here. Then, in these problems, there is one very deep and fundamental thing, which is called renormalization. And the idea of renormalization is that what you cannot see or measure should not be in your theory. So the theory has to be designed in such a way that's insensitive to inaccessible length scales. And that's what actually leads to Young-Mills as a credible equation. I don't know, so I have no idea how this would come into this scheme of things. So, renormalization. We have discovered it in dynamical systems as well, and in very interesting versions of renormalization. But they don't seem to be related to this kind of quantum field theoretical ones. Then there is this stupid infinity. So it looks like we should be able to systematically find some set of solution. It might be hard work, but if you can do it for Young-Mills, it cannot be infinitely harder for the young, it's 3 dimensions, got to 4. I mean, I'm not sure that it'll be unsurmountably harder. We already went from 1-dimensional PDEs to 3-dimensional, so I'm hopeful we could do that.